Welcome to IC, Becoming an Engineer, where we connect engineering education research with real-world practice, academia, and industry. Our goal is to create an inclusive space for dialogue, collaboration, and knowledge sharing across the engineering education sector in South Africa, positioning our unique challenges and innovations as a key voice in the global engineering education conversation. We explore the challenges and opportunities of engineering education in the Global South while linking our experiences to the broader international landscape. Whether you're an academic, industry professional, or a student curious about the future of engineering, this podcast offers meaningful discussions that go beyond research papers to unpack practical strategies for positive change. Join us as we bring together diverse voices, bridge perspectives, and reimagine engineering education for a more connected and impactful future. My name is Lilani Smith.
Hi, I'm Ruben Govender.
And today we have Professor Karin Wolff from Stellenbosch University in South Africa. And she is also the current president of the South African Society for Engineering Education. She's a distinguished researcher and educator in the field of engineering education, has a wealth of experience in academia, curriculum transformation, and industry partnerships. And we will be exploring the evolving landscape of engineering education research in South Africa, the challenges of integrating academia and industry expectations, and the future opportunities for growth in the field.
So before we begin our episode, something that both Lilani and I regularly experience in our work with Professor Karin Wolff is the way that she's able to make engineering education feel both deeply grounded and wide open. She's definitely somebody that we all admire for her theoretical grounding in education, being aware of all of the publications that are relevant to this and knowing who's written about what, but that she's also completely aware of the messiness of teaching in a classroom. And when you have students that you're engaging with, reacting with, the perfect theory and how you actually apply it is shaped by the teacher or the facilitator at the front. So Karin embodies a lot of that, and we're very fortunate to have those regular interactions with her.
Yeah, I agree. I definitely agree, Ruben. What I really appreciate is how she doesn't just talk about theory practice and the gap between those, but she really helps us to navigate it as educators, like to really understand from a very systematic perspective, how do we think about the knowledge elements, the engineering identity elements, and almost like question what counts as engineering. How do we create these connection points through the curriculum within our individual modules between the knowledge and how we want the students to integrate and embody that knowledge, and how we can move them across a different spectrum of knowledge areas that all make up engineering. And I think that's been so interesting to listen to her and the research that she's done. Even in her research, it's done in a way that's so accessible for us in the classroom to really use and make a massive difference in how we engage with our students. Welcome, Prof. Wolff, and thank you for joining us today.
I'm really excited to be here.
Okay, let's jump straight into it. We would really love to start by hearing a little bit about your journey. How did you get to where you are? What is in your background, and what are the experiences that shaped your research in engineering education?
I think that's a really important question. And especially in our space, engineering education and engineering education research, we actually seldom begin with the individual, with the people in these spaces. So I think it's really important that I do start with that. I grew up in an automotive engineering household. I was exposed to three distinctly different cultures from an early age. My father's German, my mother's South African, and I had this private school, very English, UK-focused education. And that, in a sense, already exposed me to different kinds of cultures. So I was really privileged in all ways to have had really good kind of broad science-based schooling. But I knew that I never wanted to be an engineer. My parents worked in this space. I think today that I perceived the nature of their work to be really, really tiring and really complex. And I thought to myself at the time, I'm never going to be an engineer. So, I went off to UCT and I studied drama, of all things. And ironically, it's exactly this that led me back to engineering, because my first job was in film and television, right at the point in time when celluloid was becoming digital. And as a production manager in film and television, as well as assistant director. I had multiple roles in this space. The first thing I saw was the incredible impact that all these changing technologies had on ways of working. I didn't know then that this was going to plant the seed for something else. So one, I had all these different sort of cultural experiences, different languages, different ways of doing things. Two, watching this evolving world of technology. Now, with the moratorium, as we headed towards the new South Africa in film and television, there wasn't work in the early 90s. And I ended up teaching professional and technical English in Japan for 5 years and in Germany for 6 years. And strangely enough, this whole globalization that was beginning to increase, after the fall of the wall, the whole East-West, the changes, the new South Africa, what we were seeing was increasing diversity and migration all over the show. And this gave me some kind of exposure to, one, language, making meaning across these spaces. And I realized at the time, this was both in Japan and Germany, that the resources were hopelessly inadequate. There I was teaching engineers from Japan and Germany to go to very often other European countries where English was the kind of lingua franca, or especially to go to the United States. But the textual material was about speaking English. That was when it dawned on me that it's not about speaking English. It's about speaking engineering, speaking the profession you're in. So when I got back to South Africa with those kinds of experiences and my own sort of background, I was offered a golden opportunity to start on a brand new mechatronics program at a newly merged University of Technology and to design and teach the engineering communications and then the engineering professional practice curricula for diploma students and who then became BTech students. Those are students at the level of technician and technologists. And at the time, I loved teaching and I loved working in the classroom with these students, but I intuitively from day one, because of my own work experience in the world, started to bring in the world of work to these students in the classroom. And this wonderful mentor that I had, Professor Cecilia Jacobs, said, Karin, you're an intuitively good teacher, but you know what? You need to learn the discourse. It was the first time I encountered this word discourse, the sociological word. And she helped me go off and I enrolled for my master's at the University of Cape Town. And that obviously, I fell in love with research at that stage because I'd had like 20 years of work experience. And that led me into my PhD as well. And all of those experiences led me I had this one clear question. Why is it that these students that I'm teaching and the other students that my industry partners are getting to know, why is it that industry keeps saying they can't connect theory to practice?
Thank you, Karin. That's quite a journey to get to where you are today. I'm curious, with that question in mind, how that influenced the direction that you went to in terms of engineering education research.
Okay, so when I started teaching on the mechatronics program, and I had this thing about my third years would go, ma'am, none of the stuff that we're working on, we never studied this because we had a simulated, fully project-based learning fifth semester. So in other words, half of the third year for these diploma students, they were spent in a simulated work-related environment. But I ran it because I coordinated it as under professional practice. I ran it as though they were in a real world job. So they had their spot where they sat, their team that they worked with, they had project spaces all around them, and they worked on lots of projects like today, Engineers Without Borders type projects. In those days, we had Siemens Cyber Junkyard projects, and they'd work on these projects that I could see them grappling with the complexities of these projects. And I could see that they couldn't see that thermodynamics they learned, that strength of materials they learned, all that mathematics that we half killed them with. But they weren't, one, making the connections with those in the actual work that they were doing. Okay. So while I was teaching them and now enrolled for my master's, I was really fortunate to meet Professor Carl Mayton, and he later became my PhD co-supervisor. And he at the time was working on an area called legitimation code theory. Now, literally that is what makes you legitimate in terms of the practices that you have, okay? What does the field regard as legitimate? Legitimate literally means, okay, what does the field say counts? How do you work with it? How do you sound? How do you dress? How do you show up in a space? And he developed a whole range of incredible tools to help you actually unpack what's happening in any moment of any engagement. And we call those moments knowledge practices. I mean, we're always working with kinds of knowledge. this very interview right now, there are layers and layers of knowledge that we're working with, knowledge of each other, knowledge of the technology we're working with, of the end goal that we want to achieve. Okay. And with legitimation code theory, one of his first principles that he developed and tool that he developed is actually called the semantic wave. And the semantic wave, the whole point of this is that semantics meaning meaning. When we make meaning, we can talk at a highly abstract level. I mean, we could have talked about the noise and acoustic levels in terms of this conversation we're having now at a really abstract level. But we also spoke at a really practical level about, okay, where on my computer do I click the button to change a setting from high to low, for example? Now, that movement from abstract, the calculation around acoustics, for example, and noise signals to the practicalities of what we're doing here is the link between something abstract and something concrete. And the journey between them is a wave, in a sense. But you could stop at the bottom. And I'd seen so many educators doing this. They put a principle on the board and then they go, oh, and this is an example of it. And then they put another principle on the board and they give you another example of it. That's called a downward escalator. And that's the problem in our teaching. We also have upward escalators. We start our children in school with an example of, so when you were coming to school this morning and you had 3 sweets and your friend had 2 sweets, how many sweets did you have together? That's now starting at the bottom in the real world. And we never help those kids effectively move up into the abstract of what do those look like in numbers? And now what do we do with it? So the thing with semantics and the semantic wave is that our job is to go from the concept through different steps to the real world, and then out of that real world, pull something else out, okay? And take another concept out of that, and so on. And that you build in a way that you don't forget one concept to another. Too much of our teaching is exactly like that, because we've got either downward escalators or upward escalators. What you want is a wave that builds all the time. I found that instrument, the semantic wave, and the whole principle of cumulative learning is exactly what we're meant to be doing. Real learning happens when we enable our students to connect the dots and multiple dots in ways that help them to understand why and the what and the how. So that tool, and during my master's period, I used that to look at how a group of students for my master's project were actually designing and building an air-powered vehicle for a national cyber junkyard competition. And in fact, they won that year. Ta-da! I monitored on a weekly basis and through observation and through a whole lot of strategies how they were using what kind of knowledge in what way, how abstract, how concrete, as a group collectively, what it is they were doing. And what I was interested in is what kind of knowledge were they drawing on and how were they working with it? I mean, this sensitized me to the fact that this was a mechatronics program. There was mechanical knowledge. There was electrical knowledge. There was thermodynamics. There was material science. There was programming, a lot of programming and coding. The mathematics didn't seem to be so evident, and that worried me. Okay. But I recognized that they were also working, in some of them, with mathematical ways of thinking. That whole master's project using that semantic wave opened up the space about, hang on a moment. There are different ways of thinking with different kinds of knowledge, and they're located at different points in our curriculum as a whole, and they play out in a different way when you get to the end of that curriculum or what their curriculum is intended to achieve. And that's why I started to look at the sort of curriculum as a whole. I started to become more and more interested in, why do they tell me that there's a gap between what they're doing in that third year? And why does industry say that they can't apply what they've done?
I really like that. And I think I can totally resonate with this idea of downward escalating. I feel like that was probably my mode of teaching when I started out. And I think just for those listening, we'll definitely put some resources in the link below. I think it's really nice, the way you're describing, as well as the LCT tool, to see like a visual representation of that has really been meaningful. I know in the work that we've done with you around curriculum development, and also thinking through, because now you're describing those like concrete to abstract, which I think for me, when I started engaging with you, that was very much like, oh, at least I know those two. But I think what I really like, and which I'm sure we'll get to, I hope we get to, is those fine nuances, those steps in between. That there's more steps between abstract and concrete that we often don't see as lecturers or engineering educators. So thank you for sharing that.
Can I add something? So that whole thing about academics bridging the theory to practice, and you've given us really good examples now. One of my very first collaborations, very actively in this space, was a colleague, Professor Richard Walls in civil engineering, who came to me and said, my students can't understand the concept of bracing in a structure. And in civil engineering, what makes it really different is that so much of what you see is invisible. Okay, this is true of many fields, but in a mechanical engineering context, you can set up a structure and you can actually physically show bracing, for example, or how you're holding things together. But in civil engineering, in our concrete buildings, very many of them, bricks and mortar, you're not seeing bracing at a set point so that, I don't know, the third story doesn't crumble and collapse. Now, Richard Walls came to me and he said, so here's the concept, and he gave me the mathematical equation of how you calculate bracing on a particular structure. But he'd like his students to understand it better. And through working with him, he then started to take spaghetti and marshmallows into the classroom. And in groups, students set up structures with spaghetti and marshmallows that at least, and that's one of the steps in between, Lilani, based on the comment you just made about how do you move from that abstract to the concrete. So spaghetti and marshmallows are one representational way of then simulating conceptually just what we mean by bracing. Where do you put the crossbars and the cross beams? And maybe do you use, for example, tagliatelle, dried tagliatelle, obviously, and dried spaghetti and macaroni and different things to build a pasta structure so that you can see that if you removed one of those beams, which the spaghetti now becomes, how does it collapse? That is never going to help them actually build a structure, but it is going to help plant the seed of what it is that we're looking at. Then we move to different forms of representation. So there were a whole sequence of beautiful videos at the time which showed slow motion collapsing of structures. There's another example of a step between that abstract formula or the word in principles all the way down to the real structure. Civil engineering, mechanical engineering, for example, drawings, all the schematic and diagrammatic artifacts we use are another step that helps you visualize, sometimes at a more abstract level, sometimes at a more concrete level, what the thing is that you're trying to represent. So in that semantic wave example, the steps between what we see as abstract and what is real world concrete, there are so many steps in between there. And if lecturers recognize that and harness those, they can more effectively help their students actually see the connection between that physical, practical thing and the abstract concept. But they have to build on it. So that was just an example on the side. But the thing is, at the time when I was working with all these master students, I'd noticed how that particular project group were working. I saw two of the students, it was a project group of 5, 2 on their design project would rush off to the scrapyard. We had this beautiful recycling space, and they would just take things and bring them. And they had this kind of, I called it trial and error approach. And they were not afraid of trying things and building things and breaking things. Another 2 in that project team wanted to sit down and do the calculations. And it was kind of quite linear work. I didn't have the language to explain this at the time, but I was observing this. And the 5th member of the team was constantly mediating and trying to help the 2 pairs work more effectively together. And I used to think of him as kind of the people person, but that already started planting the seed of, hang on, these students have different ways of thinking and they have different ways of responding to different kinds of knowledge. What's happening? And I started looking at all my mechatronics student academic records, and I saw the same pattern. Like half those students fell into one kind of category. They were great at the maths and science, very one answer only type people, very kind of linear, very procedural. And the other half usually often failed the maths and the science parts, but they were brilliant at adapting to the technologies and programming and like problem solving real world stuff. They could build things. They could not necessarily sit down and do the calculations behind the things they were building. And they could not necessarily construct the perfect systematic project report on that. And because I tracked them into industry, we're talking about 295 students now. Okay, by the time I finished my master's and was into my PhD, I then noticed that those students who were trial and error and plugging and playing and working with technologies, their progression in industry was far more rapid than the others. They ended up in different kinds of jobs. And I realized that my job, because I also used to mentor them and place them in industries, I started placing them in the appropriate spaces that could either grow the area that they were sort of weaker on, or that those industries could benefit from that particular student's strength. And that already started alerting me to, hang on a moment, different kinds of knowledge have different kinds of ways of thinking, and students have different orientations to these kinds of knowledge. Now okay, let me add another thing. My industry partners would often tell me, oh, please don't teach them any more calculus. Please teach them how to work with this kind of software or that kind of software, or please teach them how to do this procedural thing or that procedural thing. And we'll come back to that point later. But the issue was that I thought, I kind of want to defend what it is that we're doing with this knowledge. I'm really afraid, because there's a lot of literature on this, that if we keep teaching them only practice-based real-world technologies, we all know those technologies evolve so rapidly. They change overnight. And it's dangerous to be only teaching a kind of technology or a kind of procedure, for example. Okay. But there is something in the core curriculum that is enabling a way of thinking about something. So because I had met Professor Carl Mayton, and he then agreed to become my PhD supervisor, my co-supervisor, in fact, and he's from Australia. He was about to publish Knowledge and Knowers, this book that literally unpacks these tools that look at kinds of knowledge and kinds of knowers in a sense. All right. And I'd seen the earlier drafts. And one of the instruments or tools he created is called the epistemic plane.
Karin, so can you unpack, because let's face it, engineering lecturers are far more confident in talking about abstract things like entropy and stress than they are this quite abstract idea of the epistemic plane. So can you perhaps unpack a little bit in an engineering classroom or in an engineering learning activity, sort of what happens in this epistemic plane? How do we, where do we as the instructors sit, and like where are our students, and how do we move around?
Okay, that's an excellent question. So because this is audio only and I'm a very visual person, I'm actually going to try and help listeners understand this a little. So I want you to imagine a Cartesian plane, okay? So that's a standard, like a big plus sign.
So, big X and Y diagram.
Yes.
Right.
A big plus sign, okay, 2 axes. Now that vertical axis, the Y-axis, is the what of what we're talking about, okay?
Mm-hmm.
That's the what, and it can be the what of anything, all right? But it's the whole plane. We're talking about a knowledge practices. Now, that vertical axis, the higher you go up, the stronger, in other words, the number increases actually, but the stronger the particular what that you're talking about, a particular phenomenon. Now, what I always do in talks around this is I throw a pen up in the air and I ask people, what is this? And everybody, I've done this in Japan, I've done this in Estonia, I've done this in Australia, I've done this in South Africa. Everybody goes gravity. In whatever language they want to, that's a strong what. In other words, that is a fundamental phenomenon that is really strongly bounded. And the other end, as we go down and the numbers sort of become negative, things get weaker and weaker. So there we have, let's just think about a concept like, if I say justice, okay, or a concept like love. There are so many kinds of justice and so many kinds of love and I need a hell of a lot more information to help people understand what I mean. What's the context? Okay, that's your vertical axis. Now your horizontal axis, as I move to the right and the numbers get higher and higher, actually what this means is that the how you approach something becomes more and more fixed. It's the how you approach it that also becomes stronger. We call that side of it is like the fixed approaches side. But on the left-hand side of that horizontal axis, as I move out, it gets weaker and weaker because actually there are more and more possible approaches, more and more hows. In other words, what I'm talking about is either really fixed and strongly bounded at the top or quite weak because I don't really know what we're talking about. And how I talk about something is either really fixed, strong on the right-hand side or very open-ended on the left-hand side. That top right quadrant is about the natural sciences, the fundamental laws, the entropy and the thermoflow and the electromagnetism and all of those things. The bottom right quadrant is about procedures, whether it's scientific method or how to handle a tool or how to do mathematics. Those things don't care about what you're using them for. They're just tools. That top left quadrant is about, all of the technologies we use that can do the same thing. In other words, a host of software platforms or programming languages that all can accomplish the same thing. And that bottom left quadrant again being people and context and stakeholders and all those other things. Any good engineer is constantly thinking through all of those steps. What are the principles here? Hang on. What's the phenomenon I'm dealing with? How do I do that? How are the standard ways of dealing with that? But what's the context? What are the possibilities? What should I be doing in this context? Who do I speak to enable me to do it in that thing? So in the same way that we spoke about the semantic wave as moving up and down between abstract concepts and contexts, this epistemic plane is about moving from fixed approaches to more open-end approaches and fixed, well-known phenomena that you'd find in any textbook and real-world considerations that really, really differ. So imagine again that big cross that we drew and see yourself as talking, working your way around that all the time. There's no fixed pattern. You can start anywhere. You can start with a procedure and then go, hang on a moment, what's the principle here? Because you get lost in procedure. Or you can get stuck in the principle and go, but I can't understand this. Go to that possibilities quadrant and go, but hang on a moment. Let me take different views of this. Let me see it from different perspectives. Let me speak to the different stakeholders about that phenomenon.
So I was just thinking about, for locating my own understanding over here, not a thermodynamics teacher, but I think it might be accessible to quite a bit of the audience. Temperature is a very strongly bounded concept, right? Like you don't have to really argue with your class about what temperature means. You introduce it, they get it. Many weeks later in thermodynamics, you introduce this concept of entropy, which takes people years to begin to get a handle on. So this is an extremely abstracted concept. And that if we think about that class, we can talk about very concrete examples of let's model a power station, right? And what goes on with steam and heat, temperature and entropy, etc. in a power station. That you can show them a photograph of the boiler and all the things, but then you can abstract all of that to like this TS diagram. You can't see a boiler on the TS diagram, the temperature entropy diagram, but this line represents the boiler, but you can also, on that temperature entropy diagram, imagine processes that aren't constrained by this very, where's my turbine and my boiler, and you can move around over there in ways. Am I locating that correctly?
Absolutely. So what I'm going to do is let's take that example and make it a little more concrete. There are a lot of people who, the moment you say entropy, they get totally thrown and they're going to switch off and not listen. All right.
Indeed.
I'm going to give you a classic example from my own research here. And that is efficiency on production systems, let's say in a manufacturing environment. So we have many companies producing goods for a very competitive market, for example. And let's say they have what we call a machine, but a machine consists of multiple subsystems that produces something, okay? And they want greater efficiency on the machine. Now, in that top right quadrant of a fixed concept, in other words, a strongly bounded concept with fixed procedures, are how fast can certain things, in fact, move reasonably and stay on a production line, okay? So you've got fundamental principles like the laws of motion happening over there, motor speed, the kind of motor that you're using in your production line to enable that to move, etc. All of those fundamental principles, and I call that top right quadrant the fundamental principles, is kind of one answer because there's one phenomenon at stake. So we've got forces and we've got motion and we've got potential acceleration, or maybe you've got a control system wanting to regulate how fast and how slow, and it's a just-in-time process. So the machine, the belt itself might slow down to allow for other things to catch up, for example. All of that stuff sits in that top right quadrant. Those are fundamental principles, and you can learn them totally outside of the context of having an actual manufacturing environment. All right. Now, however, we've got this context, this manufacturing environment. It's like you asked about the turbine, where you don't know where this room is, where these different components are. A particular context has specific pieces in place in a specific way. And each of those things now has what we call routine procedures. It doesn't matter what the phenomenon is. In any factory, or any manufacturing environment, let's say that manufactures goods. You have stuff moving from one end to the other end of something. You have that stuff broken up into different components, which you can quantify. How you quantify that is quite standard. That's in that bottom right-hand quadrant, the procedures. How am I counting what my products are? What is my client expecting me to deliver? What are the protocols I follow? All of that's very proceduralized, and it doesn't matter what the phenomenon is. Principles are over there. Somebody else has designed the system. Now I follow that. However, in my factory, I can't have a single lane machine running for 16 meters. I happen to be in an environment where I need to run in a U, for example. Now, the phenomenon, the thing I want to accomplish, the speed at which I want to produce certain components or certain articles, I must do differently. So what I want to do is fixed. I want to produce the components. But the constraints of the space in which I am makes that a more open-ended problem. So now I go to that top left quadrant. Now I have different possibilities. Do I break my machine up? Do I send it along a U? What happens to my power? What happens to my production line belt? I mean, it can't actually handle that going in a U, can it? That's where the reality comes in for all of us in the engineering spaces. Where is the system that we've been teaching students about entropy or about electromagnetism or about force laws? Where is it? Mm-hmm. Can it work in that idealized way? Not necessarily. Okay, so now I'm stuck in the building that doesn't, I either go and buy a new building. Who must I ask for that? That takes me to that bottom left quadrant of that epistemic plane I was explaining. That bottom left quadrant is a phenomenon. A knowledge phenomenon is not clear, or it's not about knowledge. And the how I approach that knowledge phenomenon isn't clear, also because it's not about knowledge. It's about people and places and context and stakeholders. And when we're solving a problem, we are constantly moving around this thing. It's called code shifting. It's like walking into a space and seeing, hang on, these people can't understand my language. Let me draw it for them. That's code shifting. Or let me point it out to them. That's code shifting. Now, we just do this with the different kinds of knowledge as well. And that's what our job is. Our job in engineering education is to help our students code shift, move around that plane, build those fundamental principles and procedures. That's very important, but that it enables them to choose different procedures, different possibilities in relation to let's say, a fundamental concept that you're trying to teach them.
Like, having seen the visual representation, I think the audio is also really clear, and we will have the links in the bottom for those to look at. What's really also coming up for me is that idea of the idea that we are actually looking at making those connections for the students and organizing, perhaps in a module and across modules, those connections to be intentional. I think that's what I'm hearing, that I don't think we typically think about. We think we think in a very isolated way. We think about my module, hydrodynamics, or the Navier-Stokes equations, right? And we don't necessarily think more broadly around how do I facilitate that code shifting to develop within them. I think the other thing that's coming up for me is thinking about those quadrants. If I think about both of the right-hand side ones, they feel quite certain and safe to me to some degree as an engineer. I would say, like mathematics and science, you can trust it, at least to some degree. Let's say we can trust that knowledge is solid, like gravity is not going to shift around on us, differently from the left-hand quadrant. And I wonder if that's why we kind of typically find curriculums, I think, especially in South Africa, we find them very organized on the right. The left side seems quite complex. It takes you into that, let's really grapple with what the problem is. Let's really try and understand who these people are and what the complexities of the context are. That level of complexity, you don't necessarily see that in an engineering degree, like having debates or thinking through that level of those interconnecting points. Like, we like keeping it simple. Let's just stick to the maths and the science because we can trust that, and that's simple for us. And I wonder, and we'll hear if Ruben also has something to build on from this, but there's something that's coming in for me in terms of perhaps a missing component that we're missing in exposing our students and also exposing our lecturers. I think we teach on the right because we're comfortable there as lecturers as well. Like, it's also uncomfortable for us because we were also trained to think along those right-hand sides. And some of us at least have the experience to go across, but it's quite an uncomfortable space to move across if you're not guided, I guess, or developed or exposed in some way. So I think there's a question around how do we facilitate that learning? How do we think about academics being developed to do that? That would be interesting to hear from you. Let's hear what Ruben had in mind.
Well, so actually thinking about this and a tension between a question that we had about industry wanting specific things, but listening to Karin and thinking about my own experiences with academic colleagues, where very often academics are the ones who are incredibly constrained and say, do it this way. Like in a mathematics class, it's like, I want you to solve the equation using this technique. Whereas when you're an engineer out in the real world, your boss does not care what method you use to solve the equation. They don't even care what the solution to the equation was. They're going, what did you do with the numbers that you got at our construction site, at our factory, in our manufacturing space? Like that's the, this tension that we experience. And again, as you said, there's this academia encourages the very narrow taproot. People get more and more comfortable with increasingly complex problems in a narrow band. But when we're teaching undergraduates, you don't know where they're going to be, right? So, what Karin was saying about how do you teach them to be comfortable with being uncomfortable about their ignorance on a thing and work through it.
I think you've both made fantastic points. And what I want to do is say two things about this. On the one hand, the reason that our academics are so stuck on that right-hand side, they claim, is the large class context and assessment processes. Because if there's only one answer, well, first of all, you can run a multiple choice test for everything. Okay. If there's only one answer, you can get a whole lot of TAs or teaching assistants or tutors to help you mark against a very standardized rubric. That's one part of it. The other part of it is that as a Washington, Sydney, and Dublin Accord aligned country in our South African context, we have what our professional bodies interpret as very standard, rigid specifications for our programs. Okay, that lends itself to tick box, one answer only, fixed, specified checklists. Okay. The truth is that the standards against which our degrees, diplomas, and advanced diplomas are accredited are actually guided by the International Engineering Alliance competency profiles. And if you read the actual description of what it says that an engineering graduate should be able to do, you will see the words unfamiliar, creative, unknown, not standardized, innovative, multiple variables. All of those unknowns and uncertainties, those words around complex problem spaces, are actually in the standard. So one, they're in the IEA competency profile, and two, they're in the standard. It is what we are meant to be working towards. Any registered engineer in the world has to have gone through an accredited program, and to lead that accredited program, they have to demonstrate that they can work in unknown spaces, in complex spaces, and that they can substantiate why they're choosing what method for what, because they've considered the complex context of something. So the reality is we're actually not teaching to the level we're supposed to be teaching. Our standard quite clearly says all that uncomfortable, the discomfort in that unknown space is what we're meant to be achieving. And I think we've fallen into the trap of thinking just that the more complex we make a particular mathematical calculation, that we're somehow achieving that kind of complexity. I don't think that what we are doing is really enabling the kind of complex problem solving that is intended by the spirit of the International Engineering Alliance, and in fact, the spirit of our very own standard, So to get staff there, and I just wanted to say, so I've used these tools with staff at Stellenbosch University, at other universities around the country, and in many different spaces. And I always see them, I use these tools in my everyday living, in my whole life, every day as well. I mean, it automatically comes to me. I can see when I observe a lecturer in a classroom, wonderful semantic waiver. I saw that today. Somebody taking the principle of something and unpacking it. You see it intuitively. And when you have access to these tools, it's like having access to that moment when you grasp what entropy is. That moment you can never unsee. It's a fundamental threshold concept. And for me, these tools, these legitimation code theory tools, are like they opened up a doorway in my head to ways of seeing how things happen. And so the staff that I work with, to take them into that, from that right-hand side of that plane, as Leilani was describing, increasingly towards the left, more open-ended, actually means starting in the very way we started, getting to know themselves in the space. Who are you? What do you value? What do you enjoy? How are you seeing the world? And when you start getting staff to ask themselves about who they are in this space and what's the world in which you are, then you notice, one, that for some people, their whole world is their module, literally. And I go, where does that module fit into a program? And very often they tell me, I'm not really sure. So one of the failures, and that is because of the nature of the scientific basis of these, so all of that kind of knowledge that fits in that top right quadrant, that fundamental purist principled knowledge in a sense. The reason it's there is because for millennia, inventors and people working in the sciences have discovered and captured the magic of the phenomena in the world. And it's a really long journey to grasp all those fundamental principles. So you start protecting it. This is what this is. Everybody knows what gravity is and enthalpy and all of these things, okay? And it's like, it becomes your little silo. The specialization that emerged in all of these spaces has meant that we cut it off. It isn't something else. So that's also why it's so separate from the ways in which people are working. So when you engage staff in a conversation, locating themselves in what they're doing, and then you start stretching that conversation to, okay, so where does that module fit in a program? Where does your program fit in? What is the space in which you're running this program? Who are the students you're teaching? Where do they come from? Where are they going to? And then you also discover that the majority of our engineering academics, and I'm sorry, I have to say, this is a global phenomenon, don't know where their students are going, their graduates are going. They have not necessarily ever seen a day's work in the real engineering world. That's the way to start shifting the very staff that we're trying to enable and capacitate in terms of their own thinking. Start looking at, where does this thing that you teach in this classroom at this moment fit into the real world? Go and look at it. Chat to a friend, chat to a colleague about it. That's the beginning of that journey. And then it does lead to a very, very uncomfortable space. It's true. Okay. It leads to, oh my goodness, but now you're asking me to have all these wonderful, interesting projects with people. And I'm never going to be able to assess all of these. I'm never going to be able, what do you mean real world projects? And take a deep breath. Let's go back to, what's the fundamental principle? What are we trying to accomplish? Because you can use the epistemic plane for that as well, and not fall into just the procedures of higher education. We need to be asking ourselves, what is the fundamental principle of what we're trying to accomplish in higher education? And that's where South Africa is caught between a rock and a hard place. In other words, on the one hand, checkbox ticking and very assessment-driven approaches, very standardized things, which leads us to very procedural kinds of teaching, you know? And it's the same for our students then, that whole thing about very specific competency-based training. And Lisa Wheelahan has written extensively about this globally, by the way. We need to be really careful about just teaching how to do stuff. And currently, I think in engineering education, all we're doing is how. How do I set the exam? How do I mark it? How do I upload my marks? What am I uploading, etc.? We're not stepping back and asking why. And this whole debate about theory, practice, connections, and purpose, etc., is underpinned by the complexity of the world, the diversity in our classrooms. The globalization that we're talking about means if we are to cope with such dynamic complexity, we need to understand why, both in our jobs as higher education educators, as well as the student going out into the world and contributing, okay? And to enable that why means we need to start enabling our students to code shift and to grapple with complexity and grapple with uncertainty. And it's perfectly possible, even in such large classes. Okay, University College of London, partners in our national project, do this really successfully. Students get different kinds of projects. They actually, in their first and second and third year, for example, have the opportunity to showcase that, talk about their projects. University of Pretoria has got a really nice, successful initiative, you know, the JCP project, community engagement project, same thing. We're talking about massive classes here. We're talking about 1,600 students. It's very doable to stretch our students out into that space of discomfort and their lecturers along with them to grapple with examples of engineering in the real world. It's the assessment dilemma that seems to stand in people's way.
So I think, Karin, what's standing out for me is as you're speaking, systemically, I feel like there are a lot of markers that hold us in a certain culture. I'm thinking about, you've mentioned massification as one of them. There are a number of ways that we've always done things, ways that institutions have done things that's not necessarily challenged or questioned, or rethought. Like it's not thought through how it could be different. Because at the moment, and I mean, that's a level of complexity that an academic has to deal with. Like I want to do something that really connects and integrates this knowledge and practices for my students. And yet there are these potentially perceived constraints. They could be perceived as constraints, and they could easily be opportunities in the same breath, right? So, and that then, if I take one step back, that means that me as the individual having to engage with that needs the capacity to do that. Now, if I'm teaching a class of 1,600 and I'm oversubscribed in terms of like dealing with my students, dealing with the assessment practices, which perhaps are not the right assessment practices, which perhaps are not the most efficient assessment practices for both me and the students, but just creating that space to step back, to think through it, to share with some of my colleagues, to like understand the complexity of the situation I'm in and how can I rethink that. That's already, it feels like a luxury if we're speaking about it like now. Like institutionally, systemically, there aren't really spaces created for us as a community of educators to come together and grapple with the complexity, because this is not something you want to grapple with on your own. And most of us find ourselves quite oversubscribed, quite exhausted between the pool in terms of research and teaching, with the loads that we are teaching in the South African context. And so I think these are two factors that I think, yes, possible. And what I really love about how you've set it up at Stellenbosch University is how you have these groups. You have this recommended engineering education program. And within that program, you create this space and time with you as a knowledge expert, both in how one can set up the module in a different way, create these learning activities in a different way, think about assessment in a different way, think about the curriculum in a different way. And those groups have each other. They're together in that way. And they're moving through a year, and in some cases, then even into a second year if they're interested in starting to publish. And I think those kind of initiatives really make a difference. Also for staff to feel like we're not alone drowning in this, like our students aren't really getting it. We really want them to get it. We care so much. And sometimes in that, like, in the name of caring, we do too much and we actually tend to overwork then, as well as our students not actually getting to the learning. So I think that was really meaningful to share that complexity. I want to segue here and hear your thoughts on that.
So, I mean, you've said a whole lot of interesting things here that I think I want to pull together. So one, I was going to say, we are stuck in a space because it's comfortable and familiar. We over-assess radically. And in all our programs. And that's not just engineering, but it's particularly acute in engineering. And that is because we think that learning is not us, this is we for the, let's say, engineering educator in general. Many engineering educators think that learning happens when somebody is sitting in a classroom in front of them, looking at them, preferably with a pen and a paper or a device on which they are clearly doing what it is that is supposed to be happening in that class. But that's not when learning happens. That's the problem. That's certainly not when learning happens for the majority of our students. Learning, if we understand what learning is, then learning is happening when I have time to go through, to look at texts, to talk to people, to watch videos, to plug and play and try things, to sleep on it even. Learning is happening in all those other times. In South Africa, we have more contact hours in our engineering program than any other country. The US has 25% of the actual contact hours that we have for the same, well, not the same program, but I mean to achieve the same thing, a bachelor's in engineering. Okay. Because we are operating under the very traditional transmission-orientated fallacy that is when you're learning. I never learned a single thing by anyone talking at me. I had to see it, feel it, touch it, experiment, read by myself, work at my own pace, work with others. And there are many different ways of learning that we can see from our students. So we're killing them by putting them in a space and making them to listen to what we call flat lines. In the semantic wave terms, we talk about a high flat line. That is just an abstract, a little bit of waving at the abstract level and simple application at the top, droning on, one calculation after another. And I've sat in enough thermodynamics classes to know that that's exactly what they look like. Okay, that's not real learning. That's teaching me to plug and play with the formulas to get the right answer in an exam. I would have no idea what that looks like on the ground in the real world. Okay. In terms of if I were in building a reactor and had to work on heat exchanger, I wouldn't even know where it's connected to. Okay. So that notion that learning happens when I'm standing talking at you is a fallacy, but unfortunately it's what so many of our staff sit with. Okay. So that's number one. So the safety of believing that if they're in my class, then they're learning is also accompanied by sort of a self-indemnification. Well, you were in my class, you got no excuse for failure. Okay. So we're driving the concept of student engagement by artificially forcing students into a class and then believing that they learn. If we understood how these different kinds of knowledges worked, and particularly how they work in the engineering kinds of knowledge space, we'd know that you need a very different approach to how we use our time in an engineering program. Really. So that's the biggest challenge, that we sit our students in spaces that are poorly thought through, in the spaces themselves, for procedures that are entirely procedural. Everything we're doing in higher education is in the bottom right-hand side of the epistemic plane. We are following procedures and we have totally forgotten. I want to go back to the epistemic plane. What's the fundamental phenomenon here? What's the purpose? What is the purpose of our engineering education degrees or diplomas or advanced diplomas? What is the purpose? We have not agreed on what the purpose is, which is why it's so weak. So the what we do is not underpinned by a strong why. So all we're doing is following the rules for how. And that's the dilemma. We are caught between a rock and a hard place. With the birth of the new South Africa and massification, we had two mandates. One, we had to progress economically. And two, we had to address major social justice issues for a majority of people in the country who never had access to the kinds of education that we now, as the new South Africa, aspired to. And that meant that all our universities went, oh, wonderful. Let's be aspirational. Let's open up the top end for everybody. And everybody suddenly got access to bachelors, for example, who believed that the degree somehow is better than a diploma. Meantime, I know diplomates who leave and earn so much money. I wish I had a job as a technician. If it's a good program, then they're brilliant and they earn well. And they have engineer in the title, even though they might not officially actually be an engineer. So there's also that discrepancy of what it is we're preparing students for. So we have a really complex context in South Africa, and we're trying to do the best for all, okay, which means our resources are stretched thin, ourselves we're stretched thin, but it means going back to the fundamentals, going back to the beginning. We need to answer for ourselves, what is our purpose? We cannot fulfill industry's purpose. We cannot do what industry expects us to do without industry playing a role in what it is they want us to do. We cannot do what they expect us to do on our own. We need each other. All of this that we've been talking about has been about having the conversation, seeing different viewpoints, seeing my institution, my program, my module in the context of the bigger picture. That takes time, which, as Leilani has pointed out, we don't always have. We need to make that time. It takes resources. If we want industry partnerships, and we do desperately want them, they are literally on our doorstep. They are the very students who might have been fortunate enough to graduate last year. Hello, why are we not saying, don't you want to mentor a first year? If every graduate simply mentored one first year, not from every cohort that's graduating, but the thousands of engineering graduates out there, if we had some kind of platform, look at what technology can make possible. We'd have industry mentors of students. But it takes somebody, it takes resources, and people like us, by the way, to drive these things, to enable these things, to enable others to see why this might be important if we think that's important. So the bigger picture is, Leilani and Ruben, is that we need to have these conversations. We need to create spaces where engineering educators can come together with others, share practices, open up, change their worldviews or share their worldviews or share their strategies, build on those, bring industry into the conversation, have our ongoing conversations with students as well, because it's only together that we're ever going to solve the problem of how do we enable engineering educators to more successfully enable the very students they're trying to teach to legitimately become part of society out there. I mean, that's the question for me.
Karin, so as we're wrapping up, thank you so much for emphasizing that idea of conversations and conversations with all the different stakeholders, that it's the academic being willing to walk down the corridor to have a conversation with the person who teaches the module before and the other person in the next building who teaches the module after, and then having that, what be utterly terrifying for some of my colleagues, but this, heaven forbid, you should actually go to the engineering factory in the slightly smellier part of town and have a conversation with them about what did they value, what were their experiences, and as you said, how do we partner, because they might have some super interesting problems that we could use as training examples and that they feel that they would benefit from. And yeah, it's that, where's the awkward boundary? And how do you have people who can go walk with me to this awkward boundary and feel brave enough to walk with me a little bit past the awkwardness? So thank you so much for emphasizing those things, sharing your insights, all of the experience that you've gathered from the education space in South Africa. Every time I listen to you, I learn something more, and it makes me think a bit better about what I do in my classroom. And I suppose that's kind of key to what we're doing, is that these podcasts are for engineering educators who are wanting to do their education a little bit better. So thank you so much for that. To the listeners, we're going to have some links to some of the things that Karin has mentioned, some of the diagrams and such. And so then people can look from that and do some homework and some extra reading. And hopefully people will carry on and follow us with the further conversations that we'll be having with other practitioners in the engineering education space, and the conversations that they have and where they work, whether it's within education or these wonderful intersections of undergrad education, research and industry, etc. So thank you very much to everybody.